Okay, so I think we can start. So in the last lecture, we saw the second order reliability analysis method, at least the algorithm how to do it, we are now aware of that. You will first solve the form problem, which will give you the beta, the reliability index, the Hausdorff-Lind reliability index, and then you will calculate the kappas, the principal curvatures, and using the principal curvature you are going to update your probability of failure, right? And that is how you will be solving your reliability analysis problem using SORM, right? So we have seen this, right? So in last lecture we saw probability of failure in SORM is equal to phi of capital phi of minus beta product n is equal to 2 to capital K 1 minus beta kappa n to the power minus half, right? So this is what we saw in our last lecture. And keep in mind, although I mentioned it last time, but I will repeat it, that in books the formula is slightly different. So in book the negative sign will become positive, and that originates from the fact that we consider the direction of alpha in the opposite direction. So basically we then denote Z star is equal to minus alpha times beta, and everything originates from there. Okay. So in most books, I will say actually, in most books you will find that P of f is equal to minus beta product over n is equal to 2 to capital K 1 plus beta kappa n to the power minus half. Okay. And this happens because, as I said, how or what is the direction of alpha you are considering. Okay. And this formula is preferred, the second one, because Bruton, who developed this formula, used that notation. So in the original paper by Bruton, this is the formula that he derived, and because that is the sign convention that he took, which is the other direction of alpha as positive. Okay. But apart from that, these two formulas are identical. All you need to adjust is the sign of kappa, and you need to be consistent with your sign convention, and that is all. Okay. So this is what we discussed last time, right? What we did not complete last time, and that is something we will complete today, is that how we arrived at this formula, right? So we were discussing that. So to arrive at this, we used an approximation, and the approximation was minus beta plus epsilon is equal to phi of minus beta exponential of beta epsilon. This is the approximation that we used last time, and how this approximation holds, when this approximation holds, we started discussing that, but we never completed that. So let us complete that today. Okay. So to do that, we started with defining f as log of capital phi of x, which implied, and these are things we have done last time, so I am going a little bit faster, phi of x divided by capital phi of x. We did it last time, right? And then we started representing the log ratio, and from there we arrived at a quantity known as R of beta, right? Which was equal to m 0 semicolon beta which was equal to phi of minus beta by capital phi of minus beta, which was equal to phi of beta by capital phi of minus beta. Okay, we did it last time. And we could do the numerator switch because of the symmetry of standard Gaussian, and we discussed it last time. Okay, nothing new. You can switch it, and you can switch it because of the symmetry of the numerator, right? Symmetry of the Gaussian, the standard Gaussian about y-axis, right? So this is what we are doing. And then we are doing what we are doing after that. We actually proved, if you remember, we actually proved this thing, capital phi of minus beta plus epsilon is equal to, we already proved this thing, minus beta multiplied by exponential of r beta multiplied by epsilon. We did prove it, and we concluded that all I need to now prove is that r beta can be approximated as beta. If we can prove that r beta can be approximated as beta, we are done. And this is where we kind of stopped, although we did one or two more steps, but this is the main point where we stopped, right? So we need to show, or we need to approximate this r beta quantity, right? We need to approximate this r beta quantity. And to approximate this r beta quantity, how did we start? Can you remind me, how did we start? We started with the definition of r beta. Look at it, it is there, the denominator of that. We started with the denominator of that. So we started with this, and this is equal to integration beta to infinite phi of u du, right? And this is equal to, remind me what we did last time? Phi of u is equal to phi dash by, correct, minus beta to infinite phi dash u by u du. So this is what we did, right? And then the integration by parts, right? So that is equal to, so which implies phi of minus beta is equal to, so the minus negative sign I will keep outside, and now I will use the integration by parts. So 1 by u, integration of phi dash u will give me phi u, and this is to be evaluated from beta to infinite, right? Minus integration 1 by u, derivative of that minus 1 by u square, minus 1 by u square, and then integration of phi dash u will give me phi u du beta to infinite. This is equal to then, okay. So now let us look at the first term. Can you tell me what will that term be? What will be phi of infinite divided by infinite? I mean, what will the term be when you evaluate it at infinite? 0? Why? At infinite, standard Gaussian tends to 0, and there is a u also. So you will use the L-Hospital rule. If you use and then put it, you will get it. Okay. So you will, phi infinite will be 0. So this is equal to what? Phi of beta by beta minus 0. If I take the negative signs into account, I can switch the limits. So the first term will give me phi of beta divided by beta, and then minus and minus plus, but this minus stays, minus 1 by u square phi u du. Okay. Now, okay, by the way, this is from beta to infinite. Will you agree if I tell you that this term is greater than or equal to 0? without the negative sign? Will you agree if I tell you that this second term without the negative sign is greater than or equal to 0? Because it is an integrand of a positive quantity in a positive range, so that will be greater than or equal to 0, right? What does it mean? This means phi of minus beta is less than or equal to phi of beta by beta, right? Which means R of beta is greater than or equal to beta. Why R of beta? Because small phi of beta divided by capital phi of beta is R of beta from definition, right? And you can take the beta to the other side, so that less than will become greater than. So this I can get, okay? So at the very least you can understand this is the lower bound of R of beta, right? Now this lower bound I can always take, but I need to quantify that how much error is coming into the picture because of this lower bound, okay? So therefore we will want to quantify the, repeat, repeat, which is plus, no, minus. There are 3 minus signs. One minus sign is at the outside, okay? So yeah, so R beta will be greater than or equal to beta. So this is one of the bounds I have found out, okay? Okay, so this is one of the bounds that we could get from whatever you did till now, okay? But to actually use it, we need to also quantify how much error is coming into picture, and for that we will quantify the other bound, okay? So this is the lower bound, we need to quantify the upper bound, okay? So upper bound, and this is now new. The other part I gave some hint last time, although I did not derive it, but I gave some hint. This one I did not discuss. So let us consider this second term, okay? The second term is integration beta to infinite phi of u divided by u square du, okay, right? I am saying this is less than or equal to 1 by beta square integration beta to infinite phi u du, okay? Are you aware of this theorem? If not, just study it. I am not going to prove it, but this theorem holds, and this holds because beta square is positive, otherwise it will not hold, because beta square is positive, and yeah, u greater than beta means u square is greater than beta square. So from there, given those conditions are satisfied, this holds, okay? I will not prove it, but you can check it out. If you have doubt, you can meet me, but I am not going to prove it, but this is the other end of the bound, okay? So this is equal to then 1 by beta square, and what is the quantity inside? Integration of phi u beta to infinite, what is that? Phi, capital phi of minus beta, or 1 minus capital phi of beta, okay? So now let us take it and substitute it into the expression of phi of minus beta that we have. That is the exact expression, by the way. So we will take this bound and substitute it into that expression. So what will I get? Left hand side is phi of minus beta. Right hand side, the first term is phi of beta divided by beta. The second term is 1 by beta square phi of minus beta. What will be the sign in between? Greater than or equal to, right? Because that is that is the lower limit, right? So I can take this phi of minus beta to the other side. So if I take phi of minus beta to the other side, what will I get? Phi of minus beta multiplied by 1 plus 1 by beta square is greater than equal to phi of beta by beta, which implies phi of beta by capital Phi of minus beta, right? That is your R beta. So R beta is less than equal to beta plus 1 by beta, right? Right? So that means what did I get finally? So therefore, combining the two, I got beta less than equal to R beta less than equal to R beta plus 1 by beta. So this is the bound in which R beta resides, correct? So that means what will be the error if I take it to be the beta? The order will be beta inverse, 1 by beta, that is beta inverse, right? So therefore R beta I can write as beta plus the error will be beta inverse, right? Now assuming that beta is large, but the large is a relative term. Beta large means 3 above, 3 and above is large for beta, okay. So assuming beta is 3 or above, right? 1 by beta I can ignore, and so I will end up with R beta is equal to beta, and therefore from there we know that phi of minus beta plus epsilon will be equal to phi of minus beta exponential of beta epsilon, right? So we are finally done with the proof and everything associated with second order reliability method, okay. Now, by the way, here you can understand that I have substituted R beta to be beta, that's all I have done. So the original expression was where? Here, the second last equation. So I substituted R beta to be equal to beta, and that gave me this expression, okay. Okay, from a reliability point of view, 3 is a moderate kind of beta, so 4 is very high reliable. So 4 and above, okay. And you have to keep in mind that 4 is quite high. So when you are taking 4, then 1 by 4 will come into picture. So 4.25 will be 4, which might seem like an error, but when you go to probability of failure, that is like not that much of error. Yeah, that is not like that much of error in probability of failure terms, okay. Because ultimately your goal is to remember that this beta is used for computing the probability of failure. So when the probability of failure is in the range of 10 to the power minus 5, then beta equal to 3 is a super high. Okay, but again, for 10 to the power minus 5, beta will not be 3, beta will be 4 or something like that. Okay. So this concludes or wraps up our discussion on second order reliability method. So what are the learnings from there, from the second order reliability method? Algorithm wise, it is straightforward. You will first solve the form problem, find out beta, find out Z star, and then what will you do? You will find out kappas, and you will update your belief about probability of failure using the formula that I wrote, the Bruitung's formula. PF is equal to P of minus beta multiplied by product of 1 plus or minus kappa times kappa n times beta to the power minus half. So we'll take that and you will update your belief, right? So algorithm wise, there is not much overhead. There is some overhead to find out kappas and all those things. But when it comes to proving things, there are lots of things that are needed, and more importantly, there are lots of assumptions that are there in that, okay. Now these assumptions, as long as they hold, you will get a reasonable result. If the assumptions do not hold, then this will start giving you wrong result, okay. For example, there is a super highly nonlinear kind of function. Let's say your limit set function is x to the power 20. Then if you approximate x to the power 20 by x square for larger range of x, it is going to not work, as simple as that, right? So for super high nonlinear system, this might not work, but for moderately nonlinear system, this will still work. Okay. Computational cost, slightly more than form. Okay. Any other limitations can you think of? Smaller beta what? Why? Smaller beta. Okay. I thought smaller. For smaller beta, in reliability, less than 3 will not get. Because if you get, that means that system is about to fail. You can obviously find out reliability of some system which is in working condition. So then it can come, but you are right. That can be one of the, that is a potential reason. Anything else? You have to keep in mind that the success of this algorithm is dependent on how accurately you are finding out beta, which means how accurately you are finding out z star or x star. And that is dependent on a iterative optimization algorithm. If the algorithm do not converge, then this will be wrong. Or to be more specific, if your form results are wrong or not close by, SORM will also be wrong, because then you are not approximating about the design point, right? So in that case, it will, even in that case, it will be wrong, right? Clear? One more limitation, which is common for both this form and SORM, and you will see one problem I have given regarding that in homework 2, is that we are assuming one thing. We are assuming that a failure surface has only one design point. It is not essential. The failure surface can have multiple design points, right? And if there are multiple design points, then this algorithm will work, but not as it is. You need to find all the design points and then modify it. Okay. So this or form, even form needs to be modified. So for example, suppose in the standard normal space, my limit state function is something like I don't know, but let's say something like this, where this and these are almost equidistant or equidistant. So in that case, you need to find out both these points and both this beta. And this beta, when I am saying multiple failure point, I do not mean that they will be exactly equidistant. They are very close by. So in that case, you need to find out both and use both, and only then it will work. Okay. So you will see that I think problem 4, I think in homework 2 is a problem related to this, where we have mentioned that it has 2 or 3, we mentioned how many failure points, and then ask you to solve that problem. And if you are really unlucky, then you can have infinite failure points. Think of a circle. The limit state function is a circle about the center. Exactly equidistant, infinite number of points on the circle. And then you are doomed. Okay. You need to find all or at least most of them somehow, and then only you can do. Okay. Now you can think that I can plot and see only in 1D or 2D. If you have 100 variables, how will you plot? And your limit set function, let's say, is a finite element code, so you cannot change that. Then there is no hope, right? So there are fundamentally 2 major limitations. One is multiple failure point, and that has been addressed in the literature. You will solve it in homework 2. The second one is highly nonlinear function, and that has also been addressed, but not by SORM. For that, we have something known as higher order reliability method. So that means you go beyond second order. We are not going to discuss that. Okay.
Points are not equidistant. Let's say
almost equidistant.
We find the nearest point. If another point is close to the nearest point, then if it is above the nearest point, then halfway it is going to deviate. Like, why should I say that above the nearest point will have?
Because multimodal, right? You can see that a curve is like having multiple modes. So when you take that point, it kind of approximates about that point. So whatever is nearer is getting covered by that surface. Think about it. How are you approximating it? Like this, right? So when it is like this, and you are approximating like this, that's a reasonable approximation, I will say. When it is like this, and you are approximating, let's say, about this point, do you think the second point is even getting approximated anywhere? So that's how. So in that case, you have to combine this one with this one, and then solve it.
One of the molar will have beta value much lesser, then we can consider that thing as a design point.
If much lesser, then you don't care.
It's like these two curves are there. The second one has the less beta value.
How do you know? Okay, suppose. Okay. Okay.
If we are taking the less.
How much less is the question?
Even though not how much, like if the beta.
So I'll give you an example. Okay. Let's draw it. So let's say my limit state surface looks something like this. Okay. Then you don't care about the second one, but still you will get wrong result. Why? Because second order approximation is wrong. So it's not only, so there is not one reason that will give you wrong result. For this kind of curve, you have multiple reasons to get wrong result. The second reason is that do you think a second order polynomial will be able to approximate something like this?
When point that curve, it will give you the good result.
But do you want to find the distance to a point? Is that your objective, or your objective is to find out probability of failure? Why, if it was a given point is what all I wanted, then why did I even go for SORM? SORM was at that point. If point was of interest, we should have stick with form. Form is exact at that point, right? So is SORM. So then I should not go for SORM. So if you remember when I started discussing SORM, I showed you that how the area is getting reduced when you are doing or the error is getting reduced when you are doing a second order approximation, right? So it's not about that point. It's about the whole surface. Ideally, you should work with the exact surface, right? Yeah.
So what exactly is the issue with multiple design points? If you have multiple points with exact same value beta, what would be the issue?
The issue will be when you have multiple points. So see what you are doing. Think about it. You are finding out the design point and then approximating the curve about the design point. Why are you doing that? Because that is the zone which is likely to have the maximum chances of failure.
Will there be no problem in finding when you find out beta? We'll just get one value of beta. Will we be through form, let's say, through form will we be able to figure out that we have multiple design points, or will we not get to know that?
There are two things. If I don't tell you there are multiple failure points, it's your engineering judgment. It's more like a local optimum. Think about it like that. Local optima, can you figure out? Is there any way to find out you are at local optima or global optima? There is none, right? So same problem will persist here. So in that case, what can you do? All you can hope for is to start with different initial conditions. Instead of z star is equal to 0, you will start with different initial condition and see where it is converging and how far apart they are in terms of the distance. So that is the only way to figure it out. But if I tell you how many are there, so then you know that if you start from too far apart point, you will potentially reach those two. So finding out how many failure points are there is very difficult. But given that you know how many failure points are there, form can handle that.
Somehow we do that, we have a circle.
Then to a different story.
Like function would be very simple. Like probability distribution would be that.
Correct.
Within that radius.
Correct. You will find the area, 1 minus area. You are right. But we are not talking about finding the area. Because in form and SORM, we are not finding the area. Because finding the area is solving the integration problem, right? Which we are avoiding till now. We'll start it in maybe 5 minutes. We'll start computing the area now. And that will have absolutely no problem.
The problem is that we will not be able to understand whether there is a circle.
Yes. And that you don't care about. If you are solving the actual integral, why do you care about it is circle or not? If you are getting PF equal to the correct number. So that will have different set of problems which we'll talk about. But right now all these problems are coming up because your algorithm is dependent on finding the design point. The problem is stemming because of that. that this algorithm is designed in such a way that it depends on finding a point which is nearest, and then the whole approximation business is near that point. And that is creating the issue. If you can avoid this finding out design point business, then you are fine. I'm not saying you cannot solve it. I'm saying you cannot solve it using form and SORM, right? Okay. So again, so there are two limitations I talked about. One is highly nonlinear. It will potentially fail. Highly nonlinear. The second one I talked about is multiple MPP. And then I said that you can extend SORM to higher order reliability analysis method, and that is known as HORM, which we are not going to discuss. Okay, if you are interested, you can read it, but I will not discuss it and I will not ask question from it. So not in the syllabus, let me put it that way. Okay, but you can imagine that for second order, if it took me 3.5 lectures, for higher order I don't know how many lectures. Okay, so I do not know. Okay, but you can imagine that, right? Okay, let us move ahead.
Kappa would be in the eigenvalue decomposition in the ratio and
Okay, you can have your own other ways also. Eigenvalue is expensive to singular value decomposition. Even in eigenvalue decomposition, there are ways in which you can reduce the computational cost, because eigenvalue is expensive, by the way. But the good thing is you need to do it only once. I mean, if you do it properly, obviously, okay, and judiciously. But if you are doing it in, because ideally you should do it once it has converged. But you might say that I will find out in each iteration. Then you do it in number of times, right? Okay. Design point, most probable point, which is also known as the design point. Okay, same thing. So it's just three names: design point, most probable point, and failure point. All these three are the same thing. Okay. Now, till now, whatever we have discussed in reliability analysis comes under a common umbrella of non-sampling based approach, or sometimes also known as analytical approach. And you can understand I was trying to do everything, or we were trying to do everything analytically. Okay, and clearly these limitations I mentioned holds for, I mean, for in many cases you will not be able to get satisfactory results with this analytical approaches. And that is why there is a second group of approach, or second basket of approaches, which is known as the simulation based approaches. Okay, so next we are going to start. So this concluded our discussion on non-sampling based approaches. So the second approach is known as sampling based approach or simulation based approach. Let's write sampling based approaches. Okay. Now forget about form. There is no beta, there is no design point, there is nothing. Go back to the basics. For any reliability analysis problem, what will you have? You will have random variables and you will have limit state, and everything will be defined in terms of the limit state. That's the fundamental. So because we are done with this approximation, we don't care about other things. The fundamentals, let us go back to that. What do we have here? I have x which belongs to k dimension, right? And it's a random variable. Gaussian, non-Gaussian, I do not care. Okay. And I have a limit state function g of x, okay, is equal to 0. Okay. And then I define a failure I define as gx less than 0 and safe as gx greater than 0. We go with bad notation. Okay. Now, given this, what is probability of failure? Fundamental. What will be the probability of failure given this information? Area you were saying? Yeah, tell. Repeat. Fg. F is a function of, what is F? F of g. Who will give you f of g? It's a nonlinear function, you will never know that. F of g you cannot find out. Let's accept that and then think about it. Any idea?
Area of gx less than 0 upon total.
You will try to find out gx less than 0, and that's what he was trying to say. But now, how will you find out gx less than 0 area? You have to, no, you have to solve an integral, theory I am talking about. But that integration will not be over g, it will be over x. And it will be in which? It will be over all range of x. Which range? Only those x that are in the failure domain. So can I not write P of f as, let's see, integration in the failure domain f x x dx, right? This is what is the dimension of this integral. How many integrations are there in this equation? K. So we are talking about k dimensional integral. So a 100 dimensional integral. Clearly you cannot solve it. Okay, but before that I need to define what is omega f. So omega f is defined as all those x's corresponding to which g of x is less than 0. So this is how you define failure domain. Failure domain in terms of x, the input variable, right? Now, will you agree if I write this equation in this form? Integration over the whole domain, okay? Whole domain I or 1 gx less than 0 fxx dx. Do you agree both are same or both are different? If they are same, what is 1? Indicator function. And what will it do? Satisfied, otherwise it is 0. So this is the indicator function, right? Now what is this expression equal to? In terms of some statistical quantity you have studied, can you tell me what is this expression equal to? What is it? Expectation of what? Of the indicator function. Expectation of the indicator function, right? So this is equal to expectation of the gx less than 0, right? You agree? Now, this integration you are not going to solve. You cannot solve. Let us accept that. You cannot solve a 100 dimensional integral. Let us accept that. Okay. So what will you do? What do we do when we cannot solve an integration? Huh? That you cannot do. Let's proceed from there. 100 dimensional, you cannot work with that. Approximate with summation. In finite element, there is integration of B transpose dB. Do you solve that integration? No, you do Gauss quadrature, right? Similarly, wherever you cannot solve an integration, numerical techniques, you convert it into summation. Now remember, I am trying to find out an expectation. Law of large number allows me that I can approximate this expectation as the summation using the Monte Carlo integration. That is what law of large number allows me. So using law of large number, P of f, which was equal to expectation with respect to x, I gx less than 0. This is now approximately equal to N I have not used, right? K I was using, so let us use N as number of samples. So 1 by N summation I G of xi less than 0, where your xi is sampled from the PDF. Xi cannot be just any sample, it has to be sampled from the PDF. And we know that in the limiting condition it will match exactly with the expectation. Limiting condition means n tends to infinite, which you will never have, but if n goes to infinite, this is exact, and we are aware of that, right? So now forget about 1 by n. What is this? What do you think that summation is going to give you? Let us forget about n, 1 by n for now. So there is summation I, and what that summation will give you area? Number of failure points. Because number of failure will be 1, success will be 0. So how many times you have failed, that will be counted. Because how it is, what will it happen? That I will be added n number of times. Out of that n number of times, only when there is failure less than 0, it will give 1. Other times it will give 0. So the summation will be number of failure points. So this is then equal to NF by N. Okay. So what is it saying you? It is saying you do nothing. Just sample as many times as you can, check whether for each sample it is failing or not, count the number of failures, divide it by number of experiments you have done. Is it not how you will find out the probability of head? You will perform n number of experiments, count how many times head is there, and number of head by n. So it is the common sense answer. It is the common sense answer that you have done in any case, right? And this common sense answer is what Monte Carlo simulation does. So Monte Carlo simulation is the simplest possible algorithm that you can get. Simplest in terms of the other one took 3.5 days, this took what? 3.5 minutes, right? So in that sense, is it really simple or not? If it is so simple, why no one is using it? We're coming to that. But algorithm wise, it is the simplest you can get, and in the limiting condition, it is exact. Remember, in the limiting condition, form is not exact. It is, you cannot make it exact until and unless you change your limit set function. SORM is also not exact until and unless you make it a second order. But this is exact for any limit set function. The only condition is you need to sample enough number of times, right? So how will the algorithm look like? The simplest algorithm that we will write in this course. All limit set, assuming you can draw infinite samples. So what is the input? You have x, so fxx, you should know the PDF of the input variables in this case, because you need to sample from there, and you need to know how many times, how many samples you are going to draw. And then it's a 3-line algorithm. Set a counter equal to 0 for I equal to 1 to n. You find yi is equal to what? G of xi. Okay, sorry, first you need to sample, right? So you sample xi from fx of x, right? Xi is the ith sample, not the ith variable. Keep that in mind. From there you will find out yi, which is equal to g of xi, and then let me go to the next page. If yi is less than 0, counter is equal to counter plus 1, in the if loop, in the for loop, and then probability of failure is equal to counter divided by n, right? And if you're interested in beta, you can use you can do that phi inverse of PF, and that will give you beta if you are interested in. Okay. In some papers, beta is reported. So if you're interested, you can find it out. It will just be phi inverse. Okay. Simple, right? I mean, much simpler than whatever we have discussed till now. Okay. Now, obviously, life is not so simple. So, how many samples do you need? Infinite is theory, but in practice, what is the convergence in terms of number of samples? That you need to decide to understand. If it is converges very fast, 100 samples is very good. If it converges very slow, maybe a million sample is less. So you need to decide and find out some way to decide how many samples do we need. So let us talk about, and I will use this phrase actually, convergence rate. First of all, how do you find convergence rate of a sampler? In what term? When will you say, think about finite element, okay? When will you say that the mesh has converged? When reducing the mesh, the results would not change. When will you say number of sample has converged? When increasing the sample, the results would not change much, right? Clear? Now, when I say there should not change much, how do you quantify this change in a probabilistic settings? In probabilistic setting, what is that quantity? What is that statistical quantity? Variance, right? Variance is what quantifies change. If everything is same, variance will be 0, right? So first point is convergence rate is quantified. So convergence rate is quantified in terms of variance, actually not variance also, normalized variance. You need to normalize the variance. If all the variables were in range of 1, then 2 is a large deviation. If all the variables are in the range of 1000, then 1001 is not that big a variance. So you need to normalize it, right? How do you normalize variance? By mean, is there a name? We can coefficient of variation, right? So we do it using coefficient of variation, not variance. That's a different thing. Variation, or C dot O dot V, and this is equal to sigma by mu. Okay, I'll find out the sigma by mu and then we'll conclude. Okay, now, and sigma by mu I can find it out in this space remaining. That's enough. So sigma by mu is what I want to find out. To find out sigma by mu, you need to first know what kind of random variable it is. This performing, not X. What kind of random event do you think it is when we are looking at failure and success? See what we are doing. We are performing an experiment and checking whether there is a failure or success. Which is this experiment? Bernoulli for 1. But what are we interested in? In Bernoulli, we are interested in outcome of the event. In binomial, we are interested in number of success, number of failures. Here, what are we interested in? So it is binomial distribution, right? What is the sigma for binomial distribution? NPQ. So in this case, N, and for us, success is probability for failing. So it's opposite. So N PF 1 minus PF, and this is not your standard deviation, this is your variance. So 2 to the power half. And what is mean? NPF. What do you get after doing this calculation? This is proportional to 1 by square root of n. Because if I assume Pf is constant, then it is proportional to 1 by square root of n. What does it mean? Extremely slow convergence. 1 by n and square root of that. It means extremely slow convergence. Okay. You can do a calculation. I will do it again next time, but you try it on your own. I will not do it now. Assume Pf to be let's say 10 to the minus 4. That's a reasonable Pf. That's not a very low Pf. 10 to the minus 4. Pf is 10 to the power minus 4, right? Assume COV, target COV to be 5%. That is 0.05. Find out what is the number of n you need. What do you think the number will come around? There is a square root and all those things. So you will get in millions, I can tell you that. You will get a few millions. So few million samples will be needed if your probability of failure is 10 to the minus 4 in that range, and you want 5% confidence. If you need 1% confidence, that will go to hundreds of millions. If your probability of failure is 10 to the minus 20, it will be in 10 to the 22, 10 to the 23 number of samples we are talking about. So you understand what is happening. So 10 to the power 7 number of simulation, do you think it is even remotely possible for a realistic system? No, right? So that is why Monte Carlo simulation is the gold standard for validation, but you cannot use it in practice. As simple as that. Okay. So I'll stop here. I'll solve that problem next time. The problem I mentioned. Next time means tomorrow, right? And from there we'll go into ways of reducing this, increasing this convergence rate. Let's talk it that way, put it that way. Okay. Thank you.